as a transducer. Okay, so Turing machine acting as a transducer. And the second one that I will tell you in the question is already given in the tube, that is Turing machine acting as a adder, as well as there is another type of Turing machine that is acting as a copier. Okay, so these two questions will already be discussed in the tute. This is already discussed. Okay, so there was one doubt that I told you that I will tell you about this in the next lecture. So there was specific thing that we are not using final states in the form of when we are drawing a transducer, when we have drawn questions like one's complement and two's complement. Okay, so now, why we are not using the final state there? Because if you are seeing the Turing machine is not acting as an acceptor. Okay, so if you see what exactly is an acceptor, acceptor is suppose if acceptor is something that if you give a particular string to a acceptor, it will tell you whether this string is present in the language or this string is not present in the language. Okay, so this is as acceptor. So we are studying this finite automata, push down automata, linear bounded automata, and your Turing machine are all acceptors. But Turing machine has the functionality that it can act as many different things. It can act as a transducer, it can act as an adder, it can act as a copier, as well as it can act as a comparator also. Okay, so that is why because if you're not defining it in terms of acceptor, you will not use a final state. Okay, so if you remember that Moore and Mealy machine, again they are not the acceptor because this is they are a finite state with, I think that was finite state with output. Okay, so we are getting output from it. Okay, so that was the only reason that when you are seeing a machine as an acceptor, there will always be a final state. But when you're seeing a particular machine as a different mechanism like a transducer adder, there will not be a final state. So that is the reason in the transducer you do not I told you that in any question that is done during the transducer, there is no final state. Okay, so only we are getting output of it. Okay, just wait a second. Okay, so only when we are the Turing machine is acting as a different mechanism, there will be a not a final state. When Turing machine is acting an acceptor, there will always be a final state, because in the definition, if you see, uh, in the definition of six tuple calculus, if you remember, there are number of state and there is a final state also. So if the Turing machine, because the standard purpose of a standard Turing machine is accepting a particular string, if it is acting as a Turing machine as a acceptor, there will always be a final state. But if it is acting as a different thing, there may or may not be a final state. So keep in mind, acceptor, we always got a final state, but if a particular thing is not acceptor, there will not be a final state. Okay, so now Turing machine as a comparator. Okay, so first I tell you that how exactly to solve this question. So so in most of the question I will tell you about in universal Turing machine also, that this zero will use as a delimiter or a separator. Okay, so delimiter or a separator means that because you will be given input as a continuous forms of string. Okay, so you will always be given a input as a continuous forms of string. So what can you do? So this zero will be acting as a separator. Suppose I want, because I want to function my Turing machine as a, yes. Okay, so just let me see if anybody has question. Okay. Okay, thank you, Ishan. Okay, so now how exactly this delimiter will comes into play? Suppose I want to say that my whatever is the variable is greater than the another variable that is b. Okay, so first of all, I again use suppose a unary number system here. Okay, so in this particular question, I'm using a unary number system. Okay, so unary number system means that 1, 2, 3. It means there are this is representing 3. 1, 2, 3, 4. This is representing 4. Okay, so this is not decimal, only unary system. Okay, so I will say that my a is greater than b. It means that a has greater number of ones than b. Okay, so 3 is 2. 3 number of ones here, 2 number of ones here. So I will say that a is greater than b, and I can say that a is less than b when there are 2 number of ones here and 3 number of ones here. Okay, so when a is equal to b, I can say that the number of ones in both of them are equal. Okay, so I have to represent these numbers in a continuous form of string. Okay, so on the tape you will put like this, that 1, 2, 3, this is my A, and I will separate this input this via 0. So this is acting now as a separator. Now my B will be 1, 1. So this will be my B, and as usual there will be infinite blank symbols at the left or right of the Turing machine. Okay, so this is how you interpret these kind of questions. Okay, so the comparator will act as a greater than sign. Then when there is a greater, then there is a less than, and then there is a equal to. Okay, so we have already done equal to symbol. I think we have already done equal to, that you remember, a raised to power and b raised to power n, where number of a's and number of b's are equal to. Okay, so first I will draw this, then I will move on to this, and then I will move on to this. It's a very simple concept. Now, what exactly be the mechanism that I will be following? So for equal to, this mechanism will be simple. Okay, suppose the equal to sign will be like by 1, 1. There will be a 1, 1, and then again take 3 ones, and then there is a 0, 1, 1, 1. Okay, so whenever you're designing any Turing machine, it is always wise to take a little bit of to take an input on the tape. So that will be very beneficial to you. My starting symbol or my pointer is standing at here. So at q naught, what I'll do, what can I do? So to check that a particular input is equal to, so I can replace this with another symbol and move to the right. Okay, so now what I'll do, when there is a x, okay, when there is a 1 input, I'll change it to x and I start moving right. Okay, so this will be my first step. So it will be changed to x and it starts moving right. So at the right, this input will find any number of ones, many number of ones. Okay, so it can find many number of ones. So don't do anything when there are any number of ones, keep the ones as it is and keep moving right. Okay, so eventually you got towards this output, that is your 0. So again what you do, so you see that 0, keep the 0 as it is and keep moving right. Okay, so now you know that you are at the right hand side of the input. Now this meaning it is the starting of your B and this was your A. Okay, so now what you do, what can you do here? Now you can again mark this one as X and again keep moving left. Okay, so you can do this one, that you can mark, if after a 0 you got a 1, you mark this one as, if you want to mark this one as X. Okay, so I'm marking is a X, it's same. Okay, so I'll start moving left. Okay, so now what will happen, now you will in the path you will get zeros, axis will, you will also get axis. So I don't want to complicate this one, so I just you just let me see that what can happen. Suppose the mechanism is you replace it with the x and start moving right, and you got a 0, and then you got a, eventually you got a first one. When you got a first one, you just change it to the x and keep and start moving left. Okay, so when you move left, okay, so when you move left now, okay, so when you move left, you will get a 0 again. Okay, so now this will be again your pointer here. So that is why I'm writing it on this arrow. So only one time I will get a 0. So that is why I'm writing it on an arrow, because the 0 is only present one time. So when you get a 0 here, you again keep the 0 as it is and keep moving left. Now when you are here, you will again now you will start to see your ones and your x's. Okay, so now when you see your ones, keep the ones as it is and keep moving left. Now you will get here. Now there will be your starting x here. Now when there is a x, so you have to reach till here and you again have to move towards the right of it. Okay, so when there is a x, now again have to repeat the same procedure. So I'm just trying a loop here, so it will go towards this one. And now when it will get x, and it will keep the x as it is, and one step it will move towards right. Okay, now your pointer will be again at 1 this side. And now again the number, there is a 1, you keep this one and keep moving right. So I will again do 2 steps because there will be many things you will not see in the first step. So again now you see 1 and keep if there is a 1, see the 1 and keep moving right. Yes, there is a 0, see the 0 and keep moving right. Now in this place you will also get a number of x's here. Okay, so in this place, this q1 and q2, so when there is a 0 you will also get here a number of x's. Okay, so what you do, when there is a x, keep the x as it is and keep moving right. Okay, so that is why I follow 2 steps. Now now there will be a 1 here, so there will be a 1 here absolutely, and you can change it to 1 and start moving left. Now when you are moving left, there will also again there is a x here also. Okay, so there are number of x's. So again you have to define this part, that when you're moving left, there will be a x in the path. X, keep the x as it is and keep moving left. As now I think, yes, okay, so this was it. Yeah, now you keep moving left. Now in the left you will get a 0, so that is fine because there is only 1 0, so that is why I've written it on an arrow. So now again you will get a 1 in the path, so keep the 1 as it is and keep moving left. Okay, so now 1 and again you will get towards the starting of q0. Okay, so now you will, the pointer will be at here, keep the x. Okay, so now in the path you will get when you put the x. Now here I think you are all the, okay, so there is no need for this one. Okay, so directly you are getting a 0, so you can directly go towards this one. So 0 0 r, so now you can, your pointer will be here. Now x, now there are number of x's in here. Now the last path will be your 1. When you find a 1, you keep this as x and you start moving towards the left. Okay, so at the left you will get x's, you will get 1 0, and you will get, now here you will get no 1 here. Okay, so now what exactly will happen at this place? Now this is your q4. Okay, so now when you are moving towards the left, there will be a number of axes also. Okay, so just let me see. Okay, so I don't think I have defined this path. Okay, so I just got confused here. Exactly where were we? So we have converted it into a x here, this one. So yeah, this one. So I start moving left and there will be a number of x's. So I got here this 0 and this 0. There will be a number of ones here. Okay, so now there will be no number of ones here. So there will be no number of ones here, only there will be x's, and you will see x, there will be x's here. You keep moving towards the right. Okay, so when you are moving towards the right, okay, so I think I got confused. Just wait a second. Why I'm written right here? Okay, it is correct now. X Q2 X1 X 0 0 and it is a Q4 1 L. Then you move towards the right. Okay, so now what exactly is happening here? Just let me see second. I just got uh, now you will at here, when you are seeing this 00L, and then there will be a number of ones. Okay, so again there will be no number of ones here because all the ones are over. Now you will start moving towards the right. Why I'm moving right? Why it is written right here? Okay. Yeah, I can get towards the right here, and then okay. Oh, okay, just wait a second. I think just let me see where is the problem. I have to start again. I don't see what is the problem here. Okay, exactly the thing will be that you will start from here. Okay, so x and then x and then x and then x. Okay, so all the thing will be over. You will get here. So how will I know that my this part is equal to this part? When you are 0. Okay, so when you are at 0, so at q naught you will again get towards the starting pointer, this part. Okay, so under this path or this path, just let me see, and then you get a 0. Okay, so I will see a 0, and then I will see a 0, then I'll start moving right. Okay, so I will go towards the blank. Okay, so just let me confirm what exactly is happening, why I'm moving right here. 1 L. Okay, so 0 0 0 L, keep moving left, and there is no 1 here, but there will be a x. Okay, so when there is a x, I will move right. So okay, I'm standing at here. Okay, so now see, I got confused here. So all the things are already defined here. So when you are here, okay, 0 0 L. So when there is a 0 0 L, I am here, I am here, I will move towards the left. So I will get a x here. Now I'm standing at here. Now when you got a x, keep the x as it is and move towards the right. Okay, so that is only one step. Move towards the right. I move towards the right. Now you are standing at 0 0 r, because your all the ones are over. So when you move, when you find a x, you move towards the right. Okay, so when you move towards the right, you will immediately get a 0. Okay, so because all the x's are over, there is no one when you start starting at here, because the previous step was that there is a 1, keep there will be a number of x's in this place. When there is a 1, keep the 1 and move towards the right. Okay, so that was the step. Okay, so if you see the step, when there is a 1, you keep see the 1 and change it to x and keep move to right. Okay, so now in this step, there is no ones because all the ones are over. So I will see a 0. Okay, so I will absolutely directly see a 0, and immediately see a 0. So if you find this one, what you do, you go to another state, that is your q5, and I'm just checking that now, because all the axes here are over. Now ones here in A are over, all the ones here in B should also be over. Okay, so that is how I can tell that the this part is equal to this B part. Okay, so that is why now I am moving towards the right. Now I will see that only if there is a X, then keep the X as it is and keep moving right until you find a blank. Okay, so if you find a blank, so this will be your halting state. Okay, so if you find a blank, you can move towards, keep the blank as it is, you can move towards left or right, it depends upon you. Now this will define that your A is equal to B. Okay, so this is your halting state for q6. Okay, so I little got confused because all the inputs are over. So if you are seeing here, you can check the thing again. It is absolutely correct. Okay, so I've already written it, it's already correct. Okay, so now for A equal to B, it is now over. For A equal to B, now you have to check for A less than B. Okay, so for A less than B, what will happen? It can happen that there are like two ones and then there is a 0. So then there are three ones. Okay, so that can happen. So again, first follow all the things that you are doing here. So first you will pointer will be here and you will do it, change it to X, and you start moving towards the right. You will find any number of ones, keep moving right. You will find a z. When you find a 0, your first one, keep it as X and start moving towards left. Okay, so start moving towards left. Now again you find a one, again you find any number of X's in between, so I'm not finding here just, and now there will be again a zero, so there will be a zero here, and you see the zero and keep moving left, you will find your one here. So when you find a one, keep the one as it is and keep moving left. Now you will find a X here. So when there is a X, you keep the X as it is and start moving towards the right. And now again the same procedure will follow, and now it will convert it to again X and start moving towards right. Now it will again change it to X here, and again it will start moving left, and your zero is here. So if you find the zero, keep the zero as it is and keep moving left. Now at that point at your state Q4, there is a X, you will find the X, keep the X as it is and start moving towards right. Okay, so now you will eventually directly finding a zero. So now in this state, when you're finding a zero, keep the zero as it is and start moving right. Now it is checking that all the B part of the input is over or not. Okay, so keep moving right. Now you will find a one here. Okay, so when you're finding a one here, because if all the X's are there, it means that A is equal to B. But if you're finding a separate one, because all the A part is over and you're finding an extra one at the B part, so it means that the number of B's are greater than the number of A's. Okay, so now what you can do, you can define the state as 1, then you are finding a 1, keep the 1 as it is, and you can move either left or right, so that depends upon you. Okay, so that state will be your A less than B. Okay, so I can call this as Q7. Okay, so I think that's a little bit difficult, but if you take any example and perform this action that I've already told you, you will find all the actions add up. Okay, so now only one action is remaining, that where the number of A's are greater than the number of B's. Okay, so now in this one, what you take again another example, you can take like 3 ones and then a 0 and then a 1. Okay, so you have to analyze that at what point the number of A's will become greater than the number of B's. Okay, so you have to check again. So again, first step is change it to X, keep moving right. There will be a number of ones and zeros in the path, and there will be again when to find a first one, keep it to X and start moving towards left. And when you are seeing a left, you can again find a 0 here, and then there is a 1 in between. So keep the 1 as it is and keep moving left, and you will eventually find the X. Okay, so when you're finding X, keep the X and start moving towards the right. Okay, so when you're right, start moving towards the right, there will be a 0. So in the path there will be a number of X's. So if you find the 1, you keep the X and keep moving towards left. Now see, this is important. Now you start moving left. Now again, when you're moving left, you will find a 1, keep the 1 as it is, keep moving left. Now you will find a X, this is your X, this is your X. Now keep the X as it is and start one step towards the right. Okay, so you will take this as X. Now what will happen? Now this is very important. Now you are standing at Q1 and you find a 0. Okay, so you find a 0 and you again start moving towards the right. In between there will be number of X's, and eventually at state Q2 you will not be able to find a 1 here. Okay, so when you are not able to find a 1 here, it means that your B is over. It means that your A is greater than B. Okay, so now you can define a state here that you directly, if you only find a blank here. Okay, so if you only find a blank here, keep the blank as it is, you can move towards the left or right, but this state will be your when your A is greater than B. Okay, so that state can be your Q8 state. Okay, so again the Q6 state is similar to when the number of A's are number of B's, so that is the same automata. The only thing that is changed, that I have to tell, that the number of A's are greater than number of B's and the number of A's are less than number of B's. Okay, so when you are designing these things, you have to take an example. Okay, so you will face eventually a scenario where the number of A's are greater than number of B's. Then you will be standing at a particular state. Okay, so suppose when the number of A's are less than the number of B's, I am standing at Q5. And at the right hand side I occurred a 1. Okay, so it directly means that the number of B's are greater than the number of A's. So that is why I've defined a different state. Okay, so that is a little difficult one, and the explanation was of this question was a bit lengthy, so that is why I've discussed this particular question in the class. This question is also given in your tube, but the explanation is given to you here. Okay, so again, you can try any different combination, any combination that you want. So this will be your answer of Turing machine acting as comparator. Okay, so you remember the standard Turing machine. I've already told you the definition. Still, I just want to touch on that because this is your the transition function of your Turing machine was q into tau, and then it is changing towards a q, and then there is a tau, and it can move towards left and right. Okay, so now again, there is a very important step here that I want to tell you about, that that there are plenty of Turing machine exist. Okay, so there are many Turing machine, there are variations of Turing machine. So this is the transition symbol of a standard Turing machine. Standard Turing machine that I've already told you in the starting. You can refer to the PPT for this transition function. So there are many variations of Turing machine exist, many variations. Okay, so I'll touch some of the variations, don't worry about that, but there are many variations of Turing machine exist, but all the variations, okay, it is proved, mathematically proved, that all the variations are again not powerful than the standard Turing machine. Okay, so I'll discuss the variations of Turing machine, but they are again equivalent to the standard Turing machine. Okay, so you can change, add many functionality, add any functionality to Turing machine, it will still accept the same language that the standard Turing machine accept. Okay, so the standard Turing machine, if you remember, was I think I defined this one, that is your q into this one input, and then there is a tau, your transition symbol, then q node, and then there are two things, that is your blank, and the final state was already there. There are only two things that are new here, that is your tau and another then was in blue. Okay, so any variation to a Turing machine still is not powerful. It is equivalent to a standard Turing machine. Okay, so a variation, but do I mean by a variation? So just let me tell you. Okay, so the first variation that is also defined here, that is Turing machine with stay option. Okay, so in this exactly what exactly is happening here, the transition symbol changed here. There is only one new symbol, that is your stay. Okay, so in most of the time you will see that I will see a state, and then there is anything that is be on the tape you want to read or write. So if I just see this is your input, and I do not want to change the input, I think the one will remain as it is, and I can move towards left or towards right. You have seen this, but with this stay option, there are now three options. When you see a one, you keep the one as it is. You can move left or right, or you can stay at the same place. Okay, so that is one option added to this. Again, this Turing machine with stay option is again not powerful. It is not powerful than the standard Turing machine. Okay, so standard Turing machine, it is again equivalent to the standard Turing machine. Okay, so it is not Turing machine. If it is has an extra option, it is not powerful than the standard Turing machine. Another one is a Turing machine with semi-infinite tape. Okay, semi-infinite tape means that there is a blank symbol only on the one side. Okay, so suppose this is your tape of the standard Turing machine. This is the tape of the Turing machine. The blank is on the left and right hand side. So that tape is infinite. But in this particular case, semi-infinite means that the blank will be like, you have to define that like 1 lakh blank on the left hand side, and at the right hand side blank can be infinity. Okay, so again the power of this machine is again equivalent to the standard Turing machine. It is not powerful than the standard Turing machine. If you're seeing, the I have discussed many Turing machines, but if you want to specifically refer to the proof, you can refer to the book Peter Lind's. In that, again, the proof is also given that a particular Turing machine is how equal to another machines. Okay, so the proof is a little bit complex, so I don't think there is no need to go into that proof. So all the Turing machine was already proven that any variation of a Turing machine is again equivalent to the standard Turing machine. So there is no need to look, but if you still want to see if it for your own reference, you can refer to the Peter Lind's book. In that book, you will find there are three Turing machines, I think. Offline Turing machine, the proof is given, and multi-dimensional Turing machine, the proof has given, and there is another one. So three proofs have given, you can refer to this one. So there is another Turing machine, that is your offline Turing machine. This is offline, means that they are just giving the input from a different separate file. Okay, so suppose the input, this is your input file, and this will be your finite control, and this will be your tape. Okay, so this will be your tape. Okay, so what it will do, so the file here that is present is only read only. Okay, so you cannot make, the finite control cannot make modification here. So what it can do, it can read it from here, but it can put this whatever is read by the finite control, it can be put it on the tape. Okay, so the only difference is when we in all the Turing machine, exactly the input was not defined, that how we are giving input. In this particular Turing machine, the input that is defined here, that you have to give the input by using a specific file, and that file has to be read-only file. Okay, so you cannot do modification in the file. So you see the file and copy and paste. If you want to modify it, you first have to copy all the things from the file towards the tape, and on the tape you can make any modification, because your finite control can read or write at the same time. So that depends upon you. Okay, so offline Turing machine, there is nothing different, all the things are same, only the style of input is changed. Okay, so the input is given by a read only file. Generally we are giving input directly with a by just entering the characters or entering things, but it is specified that you can give your input in a file also. Okay, so in the same way, there is another Turing machine, that is your multiple tape Turing machine. Okay, so the transition function, if you are seeing here, it is again defining that what exactly is the meaning of multiple tape. Okay, so multiple tape means that in a Turing machine, that something like this. So this is your finite control, will be your multiple tapes that can exist. So this is your tape 1, tape 2, tape 3. It can be tape n also. Okay, so now if you're seeing the transition function, it is saying that at a finite control, so the finite control, so at one state from different tapes. Okay, so this is your tape symbol. If you're seeing, tau is your tape symbol. So there it is raised to power n, because there are n tapes, that is why it is raised to power n. So at every tape, it will be at a particular state. The state will be same for all the tapes, but the tape symbol can be different. Okay, so now the state can be changed when there is this transition, the state can be changed. So the tape, every tape can also be changed. It can move towards left or move towards right, move towards left or move towards right. Either it can read or write, it depends upon it. So every tape can individually move towards left or move towards right, and individually read or write on a particular tape. Okay, so again, if you're seeing that it looks like that, because there is a multiple tape, it can be more, it can accept more languages than a standard Turing machine, but it is not the case. Again, multiple tape Turing machine is again equivalent to your standard Turing machine that we have already discussed in the starting. Okay, so these are again the variations of Turing machines. Don't worry about this, but these are the variation that is already present there. But all the variation that you will see of a Turing machine will be equal. They are not powerful in any expressive power. They are again equivalent to your standard Turing machine. Okay, so now there is another Turing machine, that is your jumping Turing machine. Jumping Turing machine means that you are at finite control. Jumping means that if you see in any step, we again move one step towards left or one step towards right. Okay, so now the transition symbol here is again similar to Turing machine. The only thing that is changed is this. Okay, so it is saying that q multiply x multiply tau multiply left and right multiply n. Okay, so it is saying that if multiply n means that you want to jump to 2 or 3 steps. So these are the steps here. So if you want to jump to 3 steps from left, you have to define like this, that q into tau can be anything. I think suppose the tau is at a particular instance, the power tau is 1, and then you can at a tape, it is just a tape symbol, so it is 1, and you can move towards the left, and you how left you want to change, how left you want to move. I move 3 steps to the left. Okay, so that is how your it can move, or jumping Turing machine is defined. Okay, so only one thing is changed here, it is multiplied by n, and the transition symbol is very similar to the standard Turing machine. Okay, again this is not powerful than your standard Turing machine. All the variations that is present here are not powerful, they are equivalent to the standard Turing machine. Okay, so now non-resonating Turing machine is nothing but it just says that you cannot use a blank. Okay, so in every Turing machine, what can we do, that we can read the blank as well as we can also write a blank. If you're seeing in many questions, we are able to write blank onto the tape, but non-erasing Turing machine cannot write a blank on the tape. Okay, so instead of blank, it can use any other symbol like lambda, tau, or any other symbol, any Greek symbol, phi, any other symbol, but it cannot use blank. Okay, so by doing this modification also, it is not the power of this non-erasing Turing machine is not greater than the power of your standard Turing machine. Okay, so another one is your multi-head Turing machine. So multi-head can be that there is a single tape, and at the Turing machine, at the finite control, there are multiple heads like this. This is one head, this is two head. At the same tape, there can be multiple heads. Okay, so again, a multiple head can read two or more heads to read the symbol on the same tape. It can read at the same time. It can again move towards left or right at the same time. Still, it is again equivalent to the standard Turing machine. The power of this Turing machine is not increased. Again, remember it. You just keep this in mind, just by heart this thing, that any variation to a Turing machine will not result in getting more expressive power. Okay, so if a standard Turing machine is accepting L languages, the any variation of a Turing machine will again accept L languages. Okay, so it is not increased or decreased. Decreased, I will tell you about this one later. There are ways that you can decrease the power of the Turing machine, but you cannot increase, because you cannot, definitely you cannot increase the power of a Turing machine. Okay, so now the next variation is multi-dimensional tape Turing machine. So multi-dimensional is simple. The multi-dimensional wall, the tape symbol will look like this. Okay, so now your tape can move towards up, down, left, or right. Okay, so left as well as right also. Okay, so only thing, the tape placement is changed. Your finite control can be placed here. Now your transition symbol can be changed for this one as q into lambda. This is your tau, and it will can move towards left, towards right, towards up, towards down. Okay, so only two symbols are added here. Again, this does not ensure that it can increase the power of a Turing machine. It is again equivalent to your standard Turing machine. Keep this in mind. Now this is an interesting one. This is your non-deterministic Turing machine. I also want to say that your non-deterministic Turing machine is again equivalent to your standard Turing machine. Okay, so again we have discussed, I think, in finite automata, NFA and DFA is equivalent. In pushdown automata, your NPDA and DPDA is not equivalent. Okay, keep this in mind. There is an exception in PDA. I've already told you that what is the exception, that in languages like WR. Okay, so only you can make a NPDA, but you cannot make a DPDA. You cannot convert DPDA into NPDA. Keep this in mind. Okay, so now in this, if you're seeing all the symbols, the transition symbol is same. Only thing is it is raised to power 2. So this is just a power set. All the transition is written again 2 raised to power. It means that it can go towards two different state. It can put two different tape symbols onto the RAM. Either it can read or write. It can either in two copies. Okay, so in two copies it can either there can be two or more than. So it is a power set because it is raised to power 2. So it can be two or more also. Okay, so it can in either copy of a Turing machine, it can either move towards the left or right. Okay, so again it is equivalent to your deterministic. Now in this Turing machine also, your A non-deterministic Turing machine is again equivalent to your deterministic Turing machine. So NTM is again equal to DPTM. Now we are again remaining only linear bounded automata. Okay, so I will again discuss it. So again, this linear bounded automata is just what can I say? It's a toned down version of a Turing machine. Okay, so don't worry about it. I will tell you. So again, there is another thing, your NPDA with the two independent stack. Okay, so that is a very interesting thing. Okay, so if you have seen, I've already told you that you cannot parse this language with the push down automata. That if you remember this particular language, if you're seeing the if you refer to the lecture where I've told you about the pushdown automata, the transition symbol is again the similar here. The only thing that is changed here, if I just write the transition symbol of a standard NPDA, the standard NPDA I think was your only stack symbol that you start tau, and your this one was your tau star. Okay, so this was your I think your transition function for NPDA, and if you're saying that this is just 2 raised to the power of q. Now your NPDA is given two different stacks. Okay, so if you're saying this tau is from one stack, this tau is from second stack. Okay, so now what do you mean by this? Now I have already told you within one stack you can do only one comparison, either a is equal to b or a c is equal to b. Okay, so I again want to tell you that a very good question asked by a student in mail, that he asked, that's a very valid question, so I just want to share it with you also. So this particular language is a classic example of a linear bounded automata. So it is not a context free language. Keep in mind, this is not a context free language. Now the student has said that we can draw a push down automata of this particular language by pushing when you are seeing the a's. Okay, suppose when you are seeing the a's, you can push two a's. Okay, so the argument was when you're seeing the a, you can push two a's. Suppose this is one a, I push two a's. For this a, I can push two a's again. For b, I can again pop it. For b, I can again pop it. For c, I can again pop it. For c, I can again pop it. Okay, so that seems a valid solution, that you can do it like this, and your automata can be built. So this particular language should be a context free language. Okay, so that seems correct, but by designing a push down automata like this, you will also face a problem like this. Okay, so there will be a and then b and then c. Okay, so this particular string is not a part of this language, but if you follow this path, this string will also get accepted. Okay, see, when you're seeing a, you will push. When you're seeing a, you will push two a's. When you're seeing a, you will again push two a's. When you're seeing a b, you will pop it. When you're seeing a c, you will pop it. Okay, so again, this particular language will be accepted, but this is not a part of this language. Okay, so that is why I'm saying that this is a classic example of a context sensitive language. It is not a context free language, it is a context sensitive language. Okay, so in this particular case, if you're saying there are two individual stacks, okay, so the only problem is that if you got a two stacks, you can compare a and b differently and b and c differently. So it can happen. So that is why when push down automata, so this is non-deterministic push down automata, because non-deterministic push down automata is more powerful than a deterministic push down automata. When a non-deterministic push down automata is given with two stacks and that is independent of each other, it can act as a Turing machine. Okay, so that is a very interesting property. If you are saying the transition symbol is also defined here, only thing is that the two taus denote two different stacks. Okay, so this T star denotes that you can either push or pop at a particular instant. Okay, so that is a very interesting property, that a non-deterministic push down automata can also act as a Turing machine if I increase one stack. Okay, so if I increase one stack, it start to behave like a Turing machine. Okay, so that is also proven, so there is no need to check. If you want to check it, you can find it on internet. Okay, so there are many ways to prove this one. This is again mathematically proven, you can check it. but I don't think that this is already proven, so there is no need to check it. Just keep in mind that a push down or non-deterministic push down automata can also act as a Turing machine if you give a additional single stack. Okay, so that is a very interesting property. It's also an important one. Keep in mind in many competitive exams, this kind of a question is asked. Most of the student will think that a non-deterministic pushdown automata, how can this be equal to a deterministic pushdown automata? Okay, so keep this statement in mind that a non-deterministic pushdown automata can behave as a Turing machine when you give two independent stacks to it. Okay, so now another variants are your Turing machine with three states. Okay, so if you take three-state Turing machine, it can also act as a standard Turing machine. So keep in mind, and multi-tape Turing machine with stay option and at most two states. Okay, so these are again two different Turing machines that are already proven with the proof. Okay, so you if you want to see the proof, you can see it, but only in the book only there are three variations, that is your multi-dimensional or multi-head, and another one was your offline Turing machine. Okay, so only three was enough, but if you want to go it, I just take all the Turing machine that I find on the internet as well as on books. So I just merge it into the one PPT. So refer to this PPT if you want to address. There may be another variation of Turing machine also. So keep in mind, there is no variation of a Turing machine that is powerful than a standard Turing machine. Every variation of a Turing machine will accept the same language that is accepted by the standard Turing machine. Okay, so that is your variation of different Turing machines. Okay, so now there is another concept called combining Turing machine. So combination of a Turing machine is not a difficult thing. It's your just this is an example of a combination of Turing machine. Okay, so you will give two variables x and y. So again, it can be given like this one. Okay, so this can be your x and this can be your x y. So comparer or a comparator we have already defined. Okay, so if x is greater than equal to y, it can go towards the adder I have already defined. So in place of eraser you can also use a copier. So eraser is also very simple machine to build, and if x is less than y, you can go towards the eraser. Okay, so in the end you can plus these two things and your result will be this. Okay, your combining Turing machine is it's a very different thing. So what you do, it is just an example of a combination of various Turing machines. So comparator, define it differently, adder, define it differently, and eraser. So we are if you see the question that I've already made, that your comparator. Okay, so I just go to the comparator. So in this particular thing, when your a is equal to b, so you can put a adder here, so you can plus this when a is equal to b, you can add a plus b. So for adder, I have already defined this question. There are three different things. It can act as a adder, as a copier, or a transducer. So in particular state, now for this one, you just take the Turing machine that is already defined in the question, that will be discussed in the tut. Okay, so this is a component. So add all the Turing machine, all the states here. When the it is greater than 1, add all the states where a is greater than b. Add the state if it is acting as a transducer. Okay, so I just want to say that when a is less than b, I want of two ones complement of a. Okay, so you can take your a and put transducer here. When a is greater than a is greater than b, you can again put here all the individual component that you have already designed, that you are what is your it is acting as a copier. So I want to copy all the a and b, whatever is the a and b. So whatever is in the a, I want to copy. So suppose in the a is this 111, so I want to copy it 111 on the tape. Okay, so this the combination means that uh, the combination can act as this is a simple diagram. I've taken this diagram from the book of Peter Lynch. You can refer to the book. So only this is just defining that you can combine different Turing machine, because Turing machine can act as many different things. So it can act as a comparator, it can act as a adder, it can act as a eraser, it can act as a copier. So the Turing machine can act many different things at the same time. So that is why the combination of Turing machine is very, very simple, and the combination will result in very efficient circuits. So that is why the Turing machine is used to different circuits of Turing machine is very useful in digital electronics. Okay, so there are many circuits that are designed using the already designed. What they do, they design the circuit of adder differently. So they just take that coding, that the coding of it is defined, already defined, the adder coding of Turing machine, just take it and just apply one condition, that if x is greater than equal to y. Okay, so this is just an example that you can define or combine various Turing machine that we have already discussed in the previous lecture. Okay, so now this is again the formal definition of the Turing thesis that is already again discussed. So again, I've told you that the arguments of Turing thesis was that anything that can be done by or any existing digital computer can also be anything that can be done. Okay, so I think there is something missing. Okay, so anything that can be done or any digital computer can also be done. Okay, so I think there is a little bit of problem. Just let me see what exactly was the definition. Okay, so anything that can be done by existing. So there was anything that can be done by existing digital computer can also be done by a Turing machine. So I have already told you. So that definition was given in 1930. So that definition becomes so popular that your digital computer now your digital computer is referred to as a Turing machine, because they seems equal, because anything that is done by anything that is done by your digital computer can also be done by your Turing machine. So that is why. Okay, so now the another one, another point is, no one has yet to able to suggest a problem solvable what we intuitively considered algorithm. Okay, so they are saying that there is no problem that is suggested by any researcher that is solvable by a digital computer, but it is not solvable by a Turing machine. Okay, so it is just written in the formal notations. Again, this definition is again taken from Peter Lind's book, so you can refer to this on this book. Okay, so the last was alternative models have been proposed for mechanical computation, but none of them are powerful than the Turing machine. So alternate models, you have already seen that we have seen the variations of Turing machines also. Okay, so variations of Turing machine as well as another variations of digital computer again are not powerful than a Turing machine model. So that is why, because of this definition became so popular, that your digital computer is keep starting referring to as a Turing machine. Keep in mind. Okay, so another one is your universal Turing machine. Okay, so universal Turing machine I will discuss in the next lecture. Okay, so again there is one concept I want to tell you about. So any Turing machine can be represented in the form of ones and zeros. Okay, ones and zeros. Okay, so what exactly was the problem? That your digital computer can do so many things at once. Okay, so if you see that your concurrency, if you see that your modern computer can switch between tasks and can do various different tasks at one time. Okay, but your Turing machine cannot. If you're seeing here, the Turing machine actually cannot do that. So for that they have designed the universal Turing machine. So this universal Turing machine has three tapes. Okay, so this exactly there are three tapes for this universal Turing machine. So I will tell you in detail in the next lecture, but just see that they encoded what suppose suppose there is an adder here. Okay, so for this adder I can make a Turing machine. Okay, so I encode this Turing machine in this tape. I can encode this Turing machine in this tape by a stream of ones and zeros. I will tell you how. Just see that it can happen. So this Turing machine can be encoded to this, and that comes.
Excuse me, sir.
Yes, yes.
Sir, is there any quiz today?
Is there any
quiz?
Is there any quiz today? Yes, there is a quiz today, but that will be in your 1:30 lecture.
Okay, sir.
Okay. Okay, so I will discuss this thing, universal Turing machine, in the next lecture. You can move on to the next class, and thank you for listening. Again, if you have any doubt, you can just ask me.